Hello everyone, in this video we're going to talk about complexity analysis. So when we create a program to solve a given problem, or maybe to create a certain part of a larger problem, there can be many different solutions to the same problem, and not all these solutions may be equal. So for example, one solution that I create might be faster than a solution that you come up with, or a solution that you come up with might be more efficient than my solution. So if we take an example here, we've got an array here that consists of 9 numbers, and this is all encapsulated in an array. So imagine we wanted to look for the number 17, right? So that's our target number that we want to try and find. So one thing that we could do is we could start by searching this array from the first element to the last element. So we could start by looking at the number 2 and checking to see is number 2 equal to 17. If it's not, we'd move on to the next number. So the next number would be 3. We would check to see if 3 is equal to 17. It's not, so we would move on to our next number. And we could continue this on until we got to the number 17. Now if you count this up, we can see this would be one operation, this would be 2, this would be 3, this would be 4, 5, 6, 7, 8. So there will be 8 steps to this. So this is one solution. Another solution might be for us to go and get the middle value. The total amount of elements are 9, so if we go to the middle value, which would be the 5th element, which would be 1, 2, 3, 4, 5, which is 9, we start off with 9, and then we do a check here, and we check to see is 17 equal to this number, and if it's not, we want to check if it's greater or less than. So we know that the number 17 is greater than 9. So we would then go and we can cancel out all of this side of the array, because we know it couldn't be any of these numbers because these are all less. Now this given array is in order. Not necessarily every array you will be given will be in order, but for this case the whole array is ordered. So we're going to look on the right hand side here, and we'll pick the middle value again. So for this, our middle value would be 15. So 15 is not equal to 17. We want to check to see is 15 greater or smaller. So we know that 17 is greater than 15, so we can cancel out all these. And we know we're left with 2 values now. We're left with 17 and 22. And depending on what way you program your algorithm, we would then find 17, because there's no middle between 17 and 22, so you would have to pick either 17 or 22, and then you would get your outcome. So with this method, we can see that we found 17 in 3 steps, while in our previous method it took us 8. Now, I'm not always saying that this will work perfectly. For example, if we imagine we have an array like this that consists of 2, 3, 4, and 6. So imagine we have this small array, and imagine we want the number 2. We're looking for the number 2. And we go with our first approach to look at the first number. So if we do this, we can see that we've found our number 2 straight away in one step. While if we were to go the other direction and we were to get the middle value, which in this case there's no middle value, so we'd have to pick either 3 or 4. So let's assume that we pick 3. We would pick 3, and then we would be left with 2 elements, which would be 2 and 3, and then we would find 2. So this would be a longer way of doing it. It depends where the number is located in the array. So if you're dealing with smaller numbers, smaller arrays, it's usually best to go with just a straightforward approach, because it doesn't really matter. But if you imagine our array was 1,000, 10,000, 100,000, a million elements, you would see how beneficial using this other method would be. And the name given to this method up here is called binary search. But don't worry about that yet, we'll cover that in a later video. So now you can see that with a given problem we can find multiple solutions, and these multiple solutions can be better or worse, and it can be dependent on what we're looking for, the size of our array, and it can also be determined on what's important to us. So is speed important to us? Is time important to us? And I'll go into detail about time and speed later on in this video. I just want to touch on the name complexity analysis. When you think of complexity analysis, you might think of it's a guide to whether an algorithm is complicated or easy to understand from the user's point of view or from the developer's point of view. But that's not actually what complexity analysis is. For example, I could write a program and it could be very good, and what I mean by very good is, I mean it doesn't take a lot of time to execute or it doesn't take up a lot of space, but the code itself could be quite difficult for another developer to understand, or it could be difficult for me to understand it if I look back on it in 6 months' time. So just because an algorithm is really complex and it's difficult to understand and reason about the code doesn't necessarily mean that it's good or it's better. And then on the same point, just because it's really simple to understand doesn't mean that its complexity analysis is good. So when we talk about complexity analysis, we usually break it down into two types of complexity. And the two types of complexity are time complexity and space complexity. So both are important when we're developing our programs. Usually most people or most developers put more of an emphasis on time complexity. So if they have to trade off time versus space or space versus time, they usually tend to go with a better time complexity and a worse space complexity. And the reason behind this is you can go and buy more space. You can get more space by just purchasing better equipment, better machines, and there's usually no drastic effect. Now in some cases you might choose space over time, but usually you choose time over space. So you want your application to be fast. You'd rather spend that extra bit of money on the infrastructure and on the hardware and equipment and have your application running really fast. So I'll give a quick introduction to time and space. Now, to define time a little bit more in depth, we could think of time as how fast it takes a program to execute. So that definition isn't exactly right, but it's a good starting point. So for example, imagine you have a laptop that's maybe 8 years old, and imagine I have a brand new PC, a custom built PC. If I go and run the exact same program as you, my computer will run that program faster. That's just because my CPU, my RAM, my whole entire system is newer, it's faster, and because of this, it'll be able to run that program much faster than you will on your laptop that's 8 years old. So there's no point in us timing how long it takes a program because it's not going to be consistent because you don't know what type of machine it's going to be run on. So a better definition of time complexity would be how the program's time grows given a greater input. So again, if I go and give an example, it might be a little bit easier. So if we remember in maths class, we'd have graphs and we draw our graphs like this. And if we seen a line going like this, straight up, we would say that this is linear. We would say whatever sort of growth here, it's linear. So what does linear mean? It means if I take a value here, let's just say we're going to draw a box here, it's going to hit this point and it's going to go down. So if this value is 1, let's say we have an array with one input, there's only one value, and we want to perform some operation on that array. Let's say we have an array and we want to double all the numbers that's in that array. So if we just have one number in the array, let's say number 5, we're going to want to double the number 5. So we're going to return the number 10. So let's assume that that takes maybe 1 millisecond, right? So we can do that in 1 millisecond. Now imagine we have 2. So if we have 2 array items, we would see that it would execute in 2 milliseconds because again, this is a linear graph. Then imagine up here we have 5. So in our graph, so we can see it matches up. So we can see as the input grows, the time it takes grows also. But not all programs that we do are linear. Some are quadratic, some are logarithmic, some are constant. So let's go through some examples of those. So we know what a linear graph looks like. That's the one we have here. A logarithmic graph would look something like this. So we start off and we kind of start off a little bit like the linear graph, and then we start to curve. So as our input grows, so imagine on this axis here we have our array of numbers, so we have 1, we have 2, we have 5, but it's not taking us as long anymore because we've got a better solution. This is logarithmic. If this was quadratic, we'd start off similar to logarithmic and similar to linear, but then we get to a point and we start going up like this, and we go up, 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 and for our inputs, as our inputs grow, so as we go from 2 to 5, our time grows exponentially. So it's really not efficient. We want to stay away from programs or solutions that are quadratic. So one example of a type of algorithm that can be quite efficient as far as the time in time-space complexity would be a recursive function. So if you can't just remember what a recursive function is, a recursive function is a function that calls itself. So within the function itself, it calls itself again and again and again. So with this, it can be quite efficient from a time point of view. The problem is the space. A recursive function takes up a lot of additional space, and what I mean by additional space is additional memory or RAM in our computer. And the problem is, if we have a big function that we know is going to execute multiple times, we need to ensure that we have enough RAM in our system to cope with that, because if we don't have enough resources, our resources in this case being RAM or memory, we run into an error, and our error will be a stack overflow. So basically, when we see stack overflow, we know that we've run out of resources. We've run out of memory that we can use, and the program can no longer be executed. And essentially, it's crashed and it's no longer usable. Just a note that I want to add in here: when you're thinking about complexity analysis, it's really important to think about your data structures that you're going to use. So are you going to use an array? Are you going to use a hash map? Are you going to use a linked list? You want to find out what data structure works best for you and then program around that. For example, if you're using a linked list and you have some input and you want to delete an item or you want to insert an item, a linked list might be a good idea for that, because if you want to add or delete or edit in a linked list, it's called constant time. But if you want to do something like searching through a linked list, you would find that it would be much more beneficial to use a hash map. Thank you everyone for listening. If you liked the video, give the video a like. If you want to see more of this type of content, hit the subscribe button.